Okay, this is CMCET 331, Electrical Systems, Chapter 20, Light and Architectural Lighting Systems. Lighting currently utilizes 20 to 25% of our electricity usage in the US and Canada. That constitutes about 20% of the total global electrical consumption. Now, issues with this is the fact that power generated for lighting typically creates a lot of pollution in addition to greenhouse gas emissions, but lighting is crucial to performance of our everyday work and play activities. Without lighting, we'd be restrained to the hours of the day when the sun is available for us to actually have light to get anything done. So fundamental reasons for providing light in a space, the ones that we see here are to make objects visible in that space, and then also to be able to conduct activities that must take place in those spaces. So a key aspect here is that good architectural lighting has to provide the right quantity of light while also providing excellent color rendition along with minimal glare. Quality lighting tends to help improve productivity and enhances worker satisfaction. Poor lighting can actually lead to lower productivity as well as sickness in the workspace. So before we can get too much into the actual lights, we need to talk about how we actually see, because if we can't see, we're not perceiving light, so let's talk about that. So good lighting design has to involve a blend between both our scientific quantitative principles, artistic skill on a qualitative side, and then also design experience to know what's appropriate where. So in talking about how we perceive light, we need to talk about optics. This is the branch of physics that relates to the properties of light and our function of our vision. It involves the study of the human visual system and how it interacts with light. So in talking about the visual system, our visual system is composed of the eye, the optic nerve, and certain parts of the brain. In this, the eye is the organ that allows a human to sense light and it produces electrical impulses. Those electrical impulses are sent through the optic nerve back to the brain. The brain then processes these impulses. So all that's needed to transform light stimulate to nerve excitations, which allows us to view an object. And if you think about this process, it works exactly the same as a camera would, and especially our modern digital cameras. So how does our eye work? Well, it functions pretty much exactly like a camera, and by this I mean a traditional film camera. The light rays pass through the transparent cornea of the eye, and then through an opening called the pupil. Now, the size of the pupil is controlled by the iris, which surrounds it, and it opens and closes like an aperture to control the amount of light that's available. At the behind the pupil, there's a lens. The lens focuses the light, and at the very back of our eye is the retina, which holds all of the light receptors and sensors that we have back there, and those are where the image is taken in and computed into signals that are then transferred to our brain. So here we talk about the lens being behind the iris. We talk about the lens as a transparent ellipsoidal medium, and we can actually change its thickness, which allows us to focus on both near and far objects without having to actually change out our lens. So we talked about the retina as well. So now we understand how we perceive light. Next thing is we need to talk about what is light. Well, light is the visible portion of electromagnetic radiation range. So in the most basic theory, electromagnetic radiation is energy that's radiated in the form of a wave, which causes an electric field, which interacts with a magnetic field. This is similar to what we've talked about in terms of power, but it works a little different. The main idea here, though, is that the result of all of this is the acceleration of charged particles. Now, we refer to those charged particles as photons, okay? Now, within this, light tends to travel in a straight path unless it's influenced by some type of gravitational, magnetic, or some other force, so something that actually causes it to bend. An example of this would be like a black hole, which actually bends light into it because of the extreme gravitational force. Now, unimpeded, we talk about the speed of light as being around 186,000 miles per second or 300 million meters per second. Now, when we say that, we're talking about in an air or in a vacuum. If you think about a denser medium like water, it actually travels much slower. And by doing so, it actually bends the light rays because we've restricted the speed at which it can travel. That's called refraction, and we'll see a little bit of that later. So here we can see the light spectrum from the non-visible end up through our visible up to the upper end, which is not visible just as well. So everything from 0.00001 nanometers all the way up to above a meter in length. Now, of that band, we can see 380 nanometers to 750 nanometers. And if we look down here in the bottom, you can see that 380 is about right here at the bottom of the violet, and 750 is up here at the red. Now, we've got a little bit of ultraviolet down here because some people can be sensitive to that a little bit. So within here, though, if we look, that range that we're able to see is actually broken up into several different bands: red, orange, yellow, green, blue, and violet. Now, we naturally see this dispersion of visible light spectrum in nature, maybe through a prism, or if we're looking at it through raindrops, we would actually see a rainbow. Now, that works because the raindrops are bending the light due to the fact that it's a denser medium than the air, and therefore as it progresses through, we see the different gradations of color. Okay, so let's think about this now. Visible light is the part of the electromagnetic spectrum that's actually capable of exciting the receptors in the back of our retinas that ultimately end up with us saying that we've seen it. So this talks a little bit more about the 380 nanometers all the way up to the 750, which is what we see. Outside of that, we just perceive everything as darkness. Now, if we think about this, though, certain other species on our planet, dogs, cats, birds, things like that, they actually perceive light outside of the edges of the range that we have. So as an example, hawks tend to see light up into the infrared range, which allows them to sense heat a little bit more at a distance, whereas dogs can actually sense a little bit down into the ultraviolet range. So variations. It's similar to how we think about sound, whereas a dog whistle can be heard by a dog, but typically most humans cannot hear it. Okay, so let's talk about how light behaves. How does this actually work? Well, when light strikes a surface, we refer to that surface as being illuminated. Now, there's two key terms here we have to talk about. First one is illuminance. Illuminance. It's the amount of light incident or striking a surface. So we don't actually see illuminance. Illuminance is the light, like up here, where it's leaving the source and coming down and striking the surface. What we actually perceive is what's referred to as the luminance. That's the amount of light leaving an object, or to us, in essence, it's how bright an object appears. Okay? Our visual system perceives luminance, not illuminance. An easy way to remember this is that light leaving a surface is the luminance. Just use the L's there, and that helps you remember that. So now when we're talking about this, we're going to talk a little bit now about reflectance. Reflectance is what percentage of the light is actually reflected off of the surface. So if we want to think about light, light is a form of energy. So if not all the light is coming back from the surface, what's happening to the rest of it? Well, typically it's converted into heat. So as a quick example here, using this table here, you can see the different reflectances of different colors. But let's just think real quick. If I was standing in a sunny parking lot next to a white car and a black car, and I put my hands down on them, which one would I perceive as being hotter? Well, the white car would not seem as hot as the black, and the black would seem much hotter. If you look at this, that makes a little bit of sense. The white right here reflects 80 to 85% of the light incident on it, whereas the black only reflects 10 to less than 10% of the light, meaning that 90% of the light that strikes it is converted into heat. Now, we'll talk a little bit more about these colors and how this affects the way that we actually perceive color a little later on, and you'll see how this ties back. Okay. The next step is we need to talk about how light actually interacts with a surface. So first off, here we've got light striking a source. That would be our illuminance. Now, the first way it reacts to a surface is we can have reflected light. Right here, that would be the illuminance. Okay. The other two things that can happen is we can have light. The light energy can be absorbed into the surface. So this would be the percent that's not reflected. In addition, we could also have part of that percent not reflected could be actually transmitted through it. That's our transmitted light. So when our light strikes a surface, it can either reflect, absorb, or be transmitted through. Okay. Now next, let's talk about that reflected light. How does it interact with the surface? Well, if it's a nice smooth surface, think like a mirror, we're going to get a specular reflection. meaning the angle that it comes in and strikes the surface, it will reflect off at the same. Think of like a pool ball on a table. The next one we have is diffuse. Now a diffuse reflection occurs when it's a rough surface. So the light comes in and strikes it, and then due to the roughness, it broadens and spreads the light out, okay? When we're actually talking about light transmitting through a surface, if it's a clean surface like a clear piece of glass, the light will come in at one angle. Because the glass is denser than the air that it was traveling through, it will actually bend the light, or it will refract the light. And then once it's through the surface, it will refract back to the angle at which it was traveling. So what it's done here is it's pretty much offset that. This is something that you might have seen in nature, where if you look into a stream and you see a fish or some other item, it's not where you actually see it, it's actually offset just a little bit due to the refraction by the water being denser than the air. Okay? Now, that works for a smooth and clear surface. What if we have a rough or frosted surface? If you think about like frosted glass, well, the light comes in on one side, strikes, refracts a little bit, but then due to the frosting on the other side, it's actually spread out in a diffuse pattern. So you can see it's much like the diffuse reflection above. All right, next step. We've talked about how it interacts. Let's go and talk about some color perception here. So this is our ability to distinguish and interpret different wavelengths of visible light. Now, both artificial and natural daylighting sources are composed of many wavelengths, and they have varying magnitudes. So remember back when we talked about the spectrum with all the different colors? Well, we have to be able to see all that, and the light has to produce all those wavelengths for us to actually see those colors. So let's go ahead and go on to the next step. So here's an example. Look at this picture that we have down here on the bottom left. I've got a light source coming in that has all of our wavelengths in it, red, green, blue, plus all of our other colors between those. Now it's striking a red apple. The reason that we see the apple is red is because the only wavelengths of light that are reflected off of that apple are the red wavelengths. All the other wavelengths of different colors are actually absorbed by the pigment of the apple. So that's why we see the apple as red. So an example here on the right is these are the exact same strawberry. The one on the left had full spectrum light, so it had all the wavelengths in it. The one on the right, the red wavelengths were filtered out, so it almost looks like a green metallic strawberry now. So hopefully that helps you understand what's going on. So we perceive color because those are the wavelengths reflected back at us. Everything else is actually absorbed by the pigments in whatever we're looking at. So here's a good example. Here's a color. This is a low quality light, and you can see that everything is kind of gray and washed out. That's because this light does not provide a good level of color rendering. And we're going to talk about that here real quick. So let's talk about our light sources. The first off we have is what's called a chromatic light source. Now this emits a fairly even distribution of light across all wavelengths. Now, you rarely hear about anything being fully chromatic. Pretty much the only thing that is natural sunlight. Now when I say that, I'm meaning on a nice bright sunny day, no clouds in the sky. If we go outside on a nice cloudy day, we're going to end up looking like these people. Now the other option that we have out there is what's called monochromatic light. Now a monochromatic light source, it only produces visible light in a small range of wavelengths. Easiest way to describe this would be with LEDs. A red LED only puts off red wavelengths of light. A blue LED only puts off blue wavelengths of light, and green does the same for the green wavelengths. All right, let's talk about color quality now. So a light source that produces a blend of wavelengths evenly distributed across all these gives us white light. Now wait a minute, somebody's going to say that sounds a little weird. Well, because if we look back at our strawberry, you can see that we had the colors red, green, and blue. Well, that's because those are the primary colors of light. When you mix the three primary colors of light, we get white. If we did this with traditional paints like color wheels, like we might have remembered back from elementary school, typically when we mix all the colors, we either get a dark brown or a black, okay? But for us, when we have full spectrum light, all the wavelengths, we see white light, okay? So from that, white light will render all colors because it includes all the wavelengths for all the different variations of color. So generally, we consider good quality light source one that renders colors uniformly. Okay? Now, poor quality is typically what we get from something that is not chromatic or something that is fairly monochromatic at certain wavelengths. So to talk about how we're going to quantify this, we're going to use two numbers that we use to quantify our lighting sources. The first one is the color temperature of the light. The second is its color rendering index. There's a third one which talks about spectral power distribution curves, and I'll show you that in these slides, but we're not going to get into it too much. So before we can talk about those, we need to talk about one of the reasons why good lighting is important. Well, that's because of what we call our visual acuity. This is our ability to distinguish fine details. You can think of it like the keenness of our vision. How small of details can we see? So a lot of us that have corrective lenses, either glasses or contacts, this is the reason why we have those corrective lenses, so we can improve the keenness of our vision or improve our visual acuity. So if you think about this, high visual acuity is needed when we're doing very high detail tasks, so anything from reading words on a page to being able to write, to drafting, to even down further to doing sewing, or even at the highest extreme doing surgery. So as we go on here, so technically visual acuity is actually related to things like that vision test that we have at the doctor's office. So let's look at an example of that. So let's look at this. So with visual acuity, if you look at this chart, think to yourself, which are the two easiest squares to actually read? Okay, for most of you, that's probably going to be the top left and the bottom right. Now the top right, I can kind of read a little bit, but not as good as either the top left or the bottom right here. Well, why is that? It's because they have the greatest level of contrast between the detail we're looking at and the background color, okay? So that helps us understand that type of visual acuity. So before we get into the color temperature and the other items